Well, it's a great pleasure and honor for me to be here with all these distinguished people who've come from all over the world to honor and help celebrate Alex's 80th birthday, and I'm very pleased to be here. I had a very pleasurable collaboration with Alex about 15 years ago now, and it was one of the best experiences of my career. And that will be the basis of my talk, mainly. I'll talk a little bit about where that has gone since and some work that we've been doing recently, but that'll be a little bit at the end. And I have to say, Alex, that after 15 years, you look exactly the same. And I didn't have the pleasure of meeting you before 1993 or 94, but you haven't changed since. All right, so I'm real happy to be here, but I'm especially happy not to be there at the moment. This is where I'm from. That's my house. This was yesterday afternoon. I checked this morning, and that is now about there. And it doesn't look good. So I'm happy to be here, not there. My wife is holding down the fort, and she's not so happy that I'm here. But in any case, this one looks like a bad one. So this is the outline of my talk. I'll give a very brief introduction to interactions in ultracold gases, and particularly talking about the S-wave scattering length and what that means. And then our collaboration with Alex and a young guy, student, Robin Cote, who was a student of Alex at the time, and he'll be giving the next talk about this subject, which is photoassociation and interpretation of the photoassociation data in terms of scattering lengths of lithium. And then a little bit at the end on some things that we've done recently. All right, so very briefly, interactions in these ultracold atomic gases are essentially S-wave. We're dealing with things that have de Broglie wavelengths that are very, very long, like microns, in comparison to the scale of a typical interatomic interaction potential, which is more like a nanometer. And so because the de Broglie wavelength is so much larger than these interaction potentials, the exact shape, this repulsive inner core, this minimum, this long-range part, the exact shape is not so important. In fact, it gets averaged over and produces essentially a single number that you can use to describe the effect of the interactions, and that's the S-wave scattering length. And the S-wave scattering length can then be used in a mean field picture to describe the interactions in the many-body system in terms of the density in this parameter. If A is negative, that corresponds to attractive interactions, whereas if A is repulsive, that corresponds to, or positive, that corresponds to repulsive interactions. And so it's very important to know both the sign and the magnitude of the scattering length, as I'll show you in a moment, to understand what the implications of the interactions are. So in terms of a two-body picture, you can imagine some kind of a potential. Let's say we have some potential scattering. The incident wave function is here in red, and because of this attractive potential well, it sucks in the wave function into the well. There's a phase shift, and the shift then, measured in a length, is the scattering length. So the scattering wave develops this phase shift. So here's the incident waves, just a spherical wave, sine kr. This is all S-wave. There's a phase shift that comes about because of the interaction with the potential. But if you're at sufficiently low energy, you can write the scattering phase shift in terms of the wave vector k at a scattering length a. And so when you substitute that in, you can see that there's a very simple form of the scattered wave function, and there's just the shift spatially by this distance a. So what are the implications? Well, for bosons, if A is positive, you can have a stable BEC. If A is negative, on the other hand, you can see that this is negative, and there's a mechanical instability. And so it was thought that the condensate was going to collapse, and you produce little mini black holes like they're doing now, I guess, at LHC. And so people have started writing about that going back to Bogolubov in 1947 and throughout the years about the need to have positive A. For fermions, on the other hand, if A is positive, then it turns out you can have a bound state of the diatom, and that bound state is then a boson, and it can Bose-condense. And if A is negative, you have attractive interactions, and these attractive interactions can give rise to Cooper pairs. And so it's this transition from A positive to A negative, which is what has been studied in the last few years in terms of the BEC to BCS crossover of Fermi gases. So in 1994, we were trying to Bose-condense lithium-7, and so we were keenly interested to find out what the S-wave scattering length of lithium was, for obvious reasons. And in particular, we wanted to know what the sign of the scattering length was. And so the way that we were going to try to investigate this was by a new technique that had been proposed, I guess, about 7 years earlier by Weiner and Julian, called photoassociative spectroscopy of ultracold atoms. Photoassociation is an old technique, but of ultracold atoms, it was realized that it could be particularly sensitive. And the idea was to confine atoms in a MOT, magneto-optical trap, where they're very cold, temperatures like a millikelvin, where the translational energy was very small in comparison even to the line width, the natural line width of the transition. And so it was possible to do precise spectroscopy of these molecular states. And so it's a spin-and-a-half atom, and so the two spins can combine either into a spin singlet, which is this potential, or a spin triplet, which is this potential. In the excited state, I've only shown the potentials that correlate to the 2s plus the 2p1 half atom, but there's again a singlet and a triplet potential. You drive transitions, and you probe then the bound state structure of these potentials. So this is what we saw in about 1994. And being an atomic physicist, I was absolutely terrified of this. I had no idea what all of this meant. We had these various lines. If you look closely, you can start to see there are two series. There's a weaker series, which kind of peters out about there. And then interleaved is a stronger series, which goes much, much deeper, down to 2,000 gigahertz was the last state that we saw. So it's about 70 wave numbers deep. And so we had no idea what all this was. And moreover, if you looked very closely, if you look at one of these lines and you blew it up, there's all kinds of structure to that line, which turns out to be hyperfine structure. And so all of this really beautiful spectroscopy was coming out of these experiments, not only in our lab, but in other labs studying mainly sodium at NIST, and we didn't know what it was. So Alex happened to be visiting Rice in '94. I think he was visiting, well, it was either Neil Lane or John Weissite, and I can't remember exactly the circumstance, maybe John. And so I happened to see Alex, and I showed him this data, and I said, "Can you make anything of this data?" And he looks at it for a few seconds, and he goes, "Oh yeah." He says, "Yeah." He says, one of these, either the triplet or the singlet, it definitely has a positive scattering length, and the other one's probably negative. And just completely floored by that. I had no idea where all that came from. And this is one of the lessons that I learned from Alex, was that not to be afraid of these new things that maybe look complicated, but so I learned not to be afraid of molecules, but to respect them. And so Alex took this back with him to Cambridge, and he and Robin worked everything out, and we ended up writing a paper together. And this is the basic idea. This is where that first few seconds of inspiration, Alex looking at this data, this is where it comes from. So this is the scattered wave function as I described before, delta being the S-wave scattering phase shift. And you can see if A is positive, that there will be a node, at least in the asymptotic long-range region. There'll be a node in this wave function, and that node, because of the wave function overlap with the excited state, that wave function overlap will go to 0 at some places, and you should see a node in the spectra. So the idea is, in a cartoon, is here, if A is positive, then there's this node in this asymptotic long-range region. This is all inside the potential. This is much larger range. And then this is a transition to the Condon point, or the outer turning point of this excited state vibrational level. And you can see if you start coming down in vibrational level, at some point the Condon point is going to be very close to this node, and then you're going to see a node in the excitation strength. On the other hand, if A is negative, there is no node in the long-range part, and the overlap will be in general larger. And so you'll see larger signals. And so Alex was able to look at this data, and he said, well, there is probably a node in this state, in this series. That node is probably here, and if we had the foresight to have looked further, we would have seen the recurrence, seen it come back as you go through this node and go inside of it. Then you should start to see that oscillator strength return. And in the other case, was probably a negative scattering length because the transition strength much bigger and it persists much further, much deeper into the well. And so we looked for that node, and sure enough, this is another paper in this series. We looked a little bit further down. This is where the last data ended, and we took some more data, and sure enough, it did recur. That's the node. That's the smoking gun, that this is a positive scattering length. Robin is modeling of the potential, found out that this series was the singlet series, whereas the one that persists deeper into the well was the triplet series. And so there was a node in the case of a positive scattering length and no node in the case of a negative scattering length. And so all of that took Alex all but a fraction of a minute, and it took us many, many months to accumulate more of this data to prove that he was right, and then to get real numerical, quantitative numbers out of this. So what really determines the scattering length? Well, it's interesting. If you look at this potential for lithium-7, which is the boson, this is the triplet potential, happens to have a scattering length which is negative, minus 27 Bohr. If you look at lithium-6, the fermion, it has exactly the same potential. Absolutely no difference between these two. And yet the scattering length for lithium-6 is also negative, but about 100 times bigger in magnitude, which is really rather remarkable until you realize, well, what really determines the scattering length are these zero energy properties, the zero energy threshold. And what's going on is because the lighter mass in lithium-6, there's one fewer bound state. That last bound state is actually sitting just above the dissociation threshold in a zero energy resonance, and that gives rise to this scattering resonance, this scattering cross-section diverging. And so we're able to look at that with this idea, realize that what we really needed to do is to measure the binding energy of this last bound state. And that was going to be the most sensitive way of measuring these zero energy properties, these zero energy scattering properties. So that's what we set out to do. So the next year, we did a two-photon experiment. These two photons are phase-locked together, these two lasers. And by taking the energy difference between these two lasers, there's an intermediate state, so it's a Raman, stimulated Raman transition, with the intermediate state being one of these vibrational levels in the excited state. And the energy difference between these two photons then is directly the binding energy. By phase locking the two lasers together, you can get precisions of just about anything you want. We actually had a GPS antenna on our roof of our building, and just for fun, and we could measure the binding energy at about part 10 to the 8. And so that was from that, then give those numbers back to Robin and Alex, and then you get this table. So this is our final paper, where we basically summarized all of the work that we had done on both single photon and two photon spectroscopy. And the most notable thing about this table, I guess, is that for the fermion, the scattering length in the triplet state is negative, attractive, is really large. minus 2,000 Bohr. I still don't know of any atom that has, at zero magnetic field, that has this kind of as large of a scattering length. And also the boson was negative. And so the boson being negative had strong implications then about BEC for lithium-7. And so that is what comes up here. So this is our experiment back in 1995. We used a permanent magnet trap. This is now relegated to our museum in the shelf of the back room. We don't use this anymore because it forced us to use this state. This is the F equals 2, M sub F equals 2 state, which is pure triplet and therefore has a small negative scattering length. It turns out that many black holes didn't form. The world was saved. The globe didn't disappear into a big poof, but we're able to make a Bose condensate, but the number of atoms is only about 1,000. It's limited by, it turns out, by quantum pressure of the confinement of the trap. So we move forward, and in the early 2000s, the early part of this decade, we went to an optical trap where we didn't have this restriction on using magnetically trappable states, the 2-2. We instead used the 1-1. And this state has a property that the scattering length's tunable, and we could make large, repulsive, and most importantly, tunable interactions in Bose condensates. And similar work was being done about the same time in Christophe Solomon's group at the École Normale. So these are the states. This is the S1 half ground state of lithium-7. The 2-2 state is the uppermost state. It's magnetically trappable because it's a weak field seeking state, but it is pure triplet. This is the 1-1 state, which has this really nice property that the scattering length, the scattering properties are tunable by a Feshbach resonance. Feshbach resonance is a way of tuning the scattering energy into resonance with a bound state. The scattering state's a triplet, the bound state's a singlet. They have different magnetic moments. By tuning magnetic field, you can tune these into a collisional resonance, and that's what's going on here. And this one happens to be extraordinarily broad, and it has this really nice zero crossing, which has a slope of only 0.1 Bohr per Gauss. And so you can use this Feshbach resonance to make very large repulsive interactions, and so you can make condensates, but you can also make very small repulsive, small attractive, or essentially non-interacting gases. So back in 2002 at ENS and at Rice, we went on this side of the zero crossing, made the scattering length very small and negative. The condensate collapsed into solitons. This is a soliton train. Each one of these little peaks is a Bose-Einstein condensate with attractive interactions where the interactions counteract the wave packet dispersion. And so it's a soliton, just like a Kerr nonlinearity. It's exactly the same equation. And you can watch these things oscillate back and forth in a one-dimensional potential without any wave packet spreading. So right now we're using the same thing. We've come back to this, and we're studying Bose condensates in the presence of disorder, where Anderson localization requires that the interactions be very, very weak. We've been studying very weak repulsive, but also solitons in the presence of disorder. All right, so in the case of fermions, it turns out that this large attractive interaction makes it an ideal candidate for doing fermion pairing. And Hank Stope and his group and my group back in '96 proposed lithium-6 as an ideal candidate for doing an experiment where you make ultra-cold atomic Fermi gases, lithium-6, and see Cooper pairing of these. Well, later on, we identified a Feshbach resonance in the lower going state of lithium-6. This is this guy here. It's also extraordinarily broad. This is a log scale in Tesla, but this is at 800 Gauss, and it's about 300 Gauss wide. And this Feshbach resonance has now been used to study the BEC-BCS crossover over the last few years. So the interactions, the implications of the interactions for both bosons and fermions are very significant, and it was this early work in lithium that really enabled us to proceed with quantum gases in both bosons and fermions. So I want to move on now and talk about something which is a little bit more recent. This brings us up to about 2003, which is how do you make ultracold molecules from ultracold atoms? And there's been a lot of impetus to make ultracold molecules. Françoise, in her talk, mentioned that for quantum computing, for making things that have polar interactions, long-range interactions. And so you want to know what are the best ways to make ultracold molecules. And one way is to start with a gas of cold atoms and then associate them. And there are two ways to do that. You can take one of these Feshbach resonances, sweep the energy through the resonance, and in a kind of a Landau-Wiener way, bind these two atoms together. And this was described, actually, this was done first by Debbie Jin in the case of fermions back in 2003. And another way, of course, is just to do two-photon photoassociation, this Raman transition, and go directly into these levels. And in either case, if you want to do this kind of superchemistry that Françoise was talking about, you'd like to be able to do this quickly. And the free bound rates of association are very weak. You like to figure out a way to do this as quickly as possible. And therefore, you need to know, are there any fundamental or practical limitations that are imposed on the rate of association? And what determines those? So we set out to explore that, and there are several candidates that may be the things that can limit you. Quantum mechanical unitarity certainly comes into play in thermal gases. So this is the rate of association, which is the product of the density times the rate constant, which I'll call K. And for convenience, you can express the rate constant in terms of a length. And if you choose the length to be the de Broglie wavelength, and this is the unitarity limit, this just says that the scattering amplitude quantum mechanically can never be bigger than the de Broglie wavelength. Or the S-wave scattering cross-section can't be bigger than the de Broglie wavelength squared. And sure enough, if you look at a thermal gas, this happens to be from our work in 2003, but other groups have seen this as well, that you see a limitation that agrees very well with this kind of an estimate of the unitarity limit. And so the rate increases with intensity, increases linearly initially, and then it begins to roll over. Now, there's another idea, and it's wrong, but I bring it up because it's not obviously wrong. And we have a lot of arguments with various people about this, but the argument goes as follows. Photoassociation can only occur when the two atoms are close together. This is a very semi-classical picture. And so if you're going to form a molecule, the atoms have to be in close proximity with each other. And if you deplete all of the atoms in your gas that are close enough to form molecules, then there's nothing left, and the rate should saturate. And so that idea says that there's a limitation with a rate constant that looks like this. The rate is going to be proportional to the velocity of the atoms divided by their distance, their characteristic distance, which is 1 over the cubed root of the density. And for a velocity which is uncertainty principle limited for a condensate, then you get this kind of an estimate. Well, how does that compare to experiment? Well, this is an experiment that came from Paul Lett's group back in 2002, where they did photoassociation of a Bose-Einstein condensate, and they saw very high rate constants, and the rate constant that they measured was 100 times larger than that predicted by this depletion of the pair correlation. And the reason why is this semi-classical picture just doesn't work. I mean, you really have to think of this as everything is in one big de Broglie wave, and as soon as you punch a hole in the pair correlation function, it diffracts away again. You really have to think about this in terms of wave mechanics. And so this semi-classical picture is inadequate. This experiment showed that very dramatically that it was. Now, there's another idea, and this comes from Juha Javanainen and Matt Mackey at University of Connecticut. And the idea is that if you associate fast enough, that eventually you could stimulate atoms back down again, or in this, looks like in this kind of a more direct picture, you could stimulate atoms back out of the bound state into a hot continuum. And the width of this hot continuum is going to be proportional to the Rabi frequency, the rate in which you're driving these transitions. And so as you increase the intensity and you increase this association rate, the width of this transition is getting bigger and bigger, and pretty soon you're knocking atoms out of the condensate. And so this mechanism that Juha coins rogue photodissociation, kind of a large descriptor, but if that is taking place, and you have to calculate then the secret is, well, this is a very complicated process. What is that rate equal to? Well, if that rate takes place, then obviously you are limited by how fast you can associate. So it turns out that that rate comes about with a length scale which is governed by the interparticle distance. This is a universal limit, and it's independent of the association process. So it could be Feshbach association, could be photoassociation, and there's been quite a bit of theory, not only at University of Connecticut, but also in Francois' group, and Thomas Gassinger in Heidelberg, and Paul Julian and his colleagues at NIST. And so this is a very interesting process because it's in a strong coupling regime. This is a many-body effect, and it's very compelling argument that it should exist. But if you look at the previous NIST experiment, it turns out that they were very, very close to this photodissociation limit. They're right at it, and are not really seeing any signs of saturation. So this is a very curious situation, and prompted us to try to get higher rates of association where we could really probe this theory. So the way we did that was to use Feshbach resonance in combination with photoassociation. So the Feshbach resonance, because it's a collisional resonance, it means that the scattering wave function is enhanced near the atoms, and that enhancement of that scattering wave function means that the overlap can be much bigger. And so by using the Feshbach resonance in combination with photoassociation, we're able to get very large rates, very large enhancements of the photoassociation rate. And you can see it, there's a variation here of about 4 decades in the rate versus magnetic field, where the magnetic field here is in the proximity of this Feshbach resonance at 730 Gauss. So it goes to a minimum, and then it goes to the peak up here of a very high rate constant of 10 to the minus 8. And Robin, I think, will probably talk a little bit about this, and he's done some theory on this process, and I think he'll talk about that in a little bit. So the process, of course, occurs a little more rigorously. It occurs because of the enhancement of this ground state wave function at the Condon point, and if the scattering length is equal to the Condon point, this is what Alex pointed out earlier, that you have a minimum, and that's what's going on down here. So this is the minimum, and if A is very large, then this is the maximum over here. So just by varying the scattering length, you scan through this ground state scattering wave function, which changes the overlap. All right, so the point is the Feshbach resonance will strongly enhance the PA rate. We can go back to the Bose condensate now. This is a thermal gas. We can go back to the Bose condensate, tune to near the peak of this Feshbach resonance, get the strong enhancement, and see if we could see saturation in the photoassociation of a Bose condensate. And we did. So this is some data that we took earlier this year. This is a Bose condensate lithium-7. the photoassociation rate versus intensity. The intensity is rather modest if you compare to the previous experiments that I've been showing you. This is not a very high intensity, but on the other hand, being close to the Feshbach resonance, the enhancement is really enormous. And so these rate constants are an order of magnitude bigger than what we had measured before without this Feshbach enhanced rate. So the question then, obviously, is how does this maximum rate constant compare with the theory for this rogue photodissociation mechanism? And the answer is there. So we're 20 times bigger than this rogue photodissociation limit, which naively is just by dimensional arguments basically would be this value. But if you do more sophisticated theory, and Francois and Paul Julian and Thomas Gassinger and Francois' ex-student Pascal Nadon have done better theory, and that's their limit. So, and we're a factor of 7 above that. And so this is a puzzle, and this is an opportunity. I hope that if Alex if I can pique his interest, this would be a great opportunity for a collaboration that we could reunite again. I mean, this is unexplained. This is we have no idea why this discrepancy is there. So the saturation occurs actually for a much larger rate than this, a much bigger length scale. It occurs for a length scale which is the size of the Bose condensate. This is the Thomas Fermi radius and not the interparticle distance. So there's a serious discrepancy, and the question is what happened to this rogue photodissociation mechanism. So there's been some recent theory, notably by Matt Mackey, where he does two condensates, a molecular condensate and an atomic condensate. They're connected together by either two molecular condensates or atomic condensate. They're connected together by photoassociation or by a Feshbach resonance, two different molecules. And he solves this basically in a quantum optics way and gets the following result. This is the rate constant versus intensity. This is the field that we are at, and he gets actually very good agreement. He gets very close to the saturation level, and he finds that the saturation level depends, I think this is a clue to what might be going on, saturation level depends on the magnetic field. So the closer you are to the Feshbach resonance, the greater the saturation level, not really related to this rogue photodissociation, but somehow related to this enhanced wave function overlap. This is the rate constant versus magnetic field, and again, he gets this dip in very good agreement with what we see, and the kind of the order of magnitude is about right as well. You talk to Matt, he's not willing to say what this mechanism is. He doesn't really identify it physically. He said this is what comes out of calculation. So at this point, we don't really know how to interpret that. Some more recent work by Robin, a student Pellegrini. This is a thermal gas. This is a model of the experiment that I showed earlier, where we showed that as a function of magnetic field, you can get these big enhancements of the photoassociation rate constant, get a minimum when the Condon radius is equal to scattering length and enhancement at close to the Feshbach resonance. And he gets, other than this unitarity limit here, where there's a little bit of a discrepancy, everything else is really just about right on. Very impressive agreement. All right, so this is my summary. The photoassociation is a wonderfully sensitive tool for determining the interactions of ultracold atoms. So one can do either one photon or two photon photoassociation, learn in quantitative detail what the scattering lengths are. You combine that with locations of Feshbach resonances, fields where the Feshbach resonances occur, and you can really map out these potentials extraordinarily well. I think we're now sensitive to things like the long-range coefficients that people have been talking about earlier at a detail that was not possible with more conventional spectroscopy. So you can achieve very strong photoassociation by going to a Feshbach resonance, and that gives rise to saturation in the Bose-Condon state, but at a much higher level than predicted. So I want to conclude by wishing Alex a happy birthday, and I want to thank him for the opportunity of our collaboration. Many years ago now, it was still is one of the most enjoyable and productive experiences of my career, and I'm very grateful for it, and I hope that we can resolve this new problem, and I can come back and talk about it at your 90th birthday. Thank you.
You said the semi-classical picture breaks down because it predicts the photoassociation rate, which is very low. But if you would replace the velocity by... For the velocity in a Bose condensate, you use the velocity given by the big wave function. But if you sort of start to modify the wave function by photoassociation, you create little whatever holes in the system, then you may have kind of modulations of the wave function on a scale of the interatomic spacing, and you could actually just use the semi-classical formula and plug in a velocity which corresponds to the Broglie wavelengths, which is the interatomic spacing. Mm-hmm. And then actually the semi-classical picture and the quantum picture with the rogue photoassociation would predict the same scaling.
Yeah, I agree. You might be able to cook up a fix to the semi-classical picture that makes it agree, but it's probably better just to start with quantum mechanics.
Maybe what I said was just a dimensional argument, and for dimensional reasons, if there are only so many length scale you can put together. But
yeah.
I have one question myself. Would there be a way of measuring the pair of hot atoms when you do rogue photoassociation? You create pairs of hot atoms, and nowadays it is possible to detect the atoms out of a condensate. For instance, the experiment of Chris Westbrook in Orsay on metastable helium is detecting atoms going out of a condensate. Could you do that?
Well, okay, that's a great question. With the metastable atoms, of course, you have the advantage that the detectability is at the single atom level. You can detect, because it's metastable, when it hits a charged particle detector, it ionizes, and you can detect it with unit efficiency. We can't do that. And the rate of the production of these hot atom pairs is so low on the scale of things that a few atoms dribble away during, it would take a few milliseconds for them to escape the interaction region. And in that few milliseconds, there might only be a handful of atoms that are leaving in any given time period. So the signal would be extraordinarily low, and it would be, I'm afraid, far below our detectability. But in an experiment with a metastable atom, it would be possible.
So it's restricted to metastable atoms. Okay. Okay.
I have another question. You made me curious about it when you discussed the sort of fundamental limit of photoassociation. And at least the way how I understood your argument, the Feshbach resonance was just the experimentalist trick to get, with the available laser power, a sufficiently high rate that you could see the saturation. So let me now turn that into maybe a hypothetical question. Assuming you had infinite laser power and you could observe saturation at different magnetic fields for different scattering lengths, would you, or do you have indications that experimentally the saturated rate is sort of universal and only depends on a length scale of the condensate, whether it's the Thomas Fermi radius, whether it's the interatomic spacing or something else? At least the way how you present it the scattering length itself did not enter the argument for saturation? And what does the theory say about it?
Yeah, so that's a great question, and that would help resolve what the origins of the process are. And after seeing Matt Mackey's calculation, we realized that would be a great experiment to do, to look at saturation versus scattering length. This is exactly what Matt is predicting, that the saturation level will change with scattering length. We haven't done it. We're doing something else at the moment. Maybe we'll come back, but at the moment we're not doing it.
Any other question? Yes?
The thing that strikes me there is that experimentally the scattering length is extremely sensitive to what you're doing, and we've known that from calculations as well. And I wonder, you were relating the scattering length to the binding energies, and should one really be talking about binding energies that could be, you can say precisely what the binding energy is, whereas the scattering length is artificially sensitive because it's an arctangent in the theoretical formulation.
You mean directly relate the scattering length to the binding energy?
Yes, of course it only works when you've got it closely.
We have not analyzed it that way. I know Robin and in our work, we made a model potential and we adjusted the parameters of the model potential so that the binding energy agreed with what we measured. So it was more indirect than what you described. But it seems like maybe Robin could answer this better, but or Alex, but it seems like by doing that you could get an answer, but it may be not as sensitive, as accurate as doing the whole potential.